Hi everyone, today I've got a new problem and of course I want to offer a nice solution. This comes from a member of AdamBlockStudios. I was presented this particular issue and I'd like to show you actually what his comments are so you can see the way it was presented to me, and then of course I'll show you the problem and kind of how to solve it. So the issue is that I received this email and it said that he has this tricky either light leak or reflection problem, and it is a kind of scattered light issue that shows up in his data of NGC 7497. He has some beautiful data of this field of view. And he says it's not so bad, but he'd really like to get rid of it. He knows that he can really do some brute force methods of doing this, but, and this is the part that really got me excited, is he said he wanted something more precise, something more elegant, and that really lends itself to the kind of philosophy of what I'm trying to do at AdamBlockStudios. I'm trying to offer not only the workflow, I mean, how do you put together all of this cool data, make it kind of go together, not just the steps. I'm trying to illustrate problem solving. Although this might not be your problem, it's a problem that the technique for solving it can be used in many different ways. And of course, if you ever do have the problem, then you have kind of an exact way of going about solving it. And so I hope that that is a different way, a different kind of thing that AdamBlockStudios offers, and I encourage you to check it out. Now, let's go ahead and look at what the problem is here. We'll look at his data. So he has what is the beginnings of an LRGB image, and like I said, really beautiful data of this field of view. You have the clouds of dust, you have the wonderful galaxy, everything you could hope within this data. But if we create a color picture out of his RGB data, now it hasn't been in any way calibrated, like not using color calibration, so this will be just the raw combined color information. We'll use a channel combination here. And let's see what the color image looks like. I have the channels unlinked here, so that when I display them, we'll see if I link them, so you can see it's not going to be pretty. It'll just be kind of a muddy mess. So let's unlink them, and we'll optimize the screen stretch for each of the channels. Still not a very pretty color picture yet because it hasn't been color calibrated, but you can see what the issue is. The issue is that we have this stuff showing up in the image. It is probably a specular reflection from some shiny surface that's just outside the chip, so light, from stars, it falls not only on the chip, but in areas just, surrounding, immediately adjacent to the sensor. And if any little surface has a little metal, something shiny, or some other thing that could scatter or refract or diffract light, then you get problems like this. A very common kind of problem. What is nice about this, and this is why I took on the kind of the challenge, is that anytime you have a problem that you can isolate in either color or brightness or some other attribute, that is going to give you purchase, the ability to find some solution that is probably going to be more exact, elegant, precise, just like what the gentleman's name is Jonathan, just like what Jonathan was looking for here. So it is indeed that is my way of thinking about this. The fact that that is green and blue only means I'm not going to see it in either the red data or, and this is surprising to me, it didn't even show up in the luminance data either. So let's actually do that. Let's blink these two images just so you can see that the issue really only shows up in those particular color bands, which is very nice as it so happens. So if we blink the images, you can see down here, and I'll just zoom in and show this in a little more zoomed way, that the image really is isolated to those particular colors, and that has a fortuitous thing for us. All right, so let's take advantage of that. What I'm going to do is show you a technique that anytime you have a problem like that you can isolate in either brightness or by color, you might be able to use this thing that I'll show you next. All right, so the first thing I'm going to do that I think is going to help the technique is I'm going to go ahead and apply DBE to these images. Now, normally when I use DBE, I do it on a full color image because you're basically applying it to each of the color channels, 3 channels, simultaneously. Here, I'm just going to do them individually. I'm not going to yet combine anything to make a color picture. I think we can employ this technique on the grayscale images themselves. That'll be the best way of doing this. So I'm going to run DBE here. Let me find DBE. And I'm going to apply it. Let's go ahead and just use the green image, our problem image. I'm not going to be very careful about this. The way I'm going to do it is to make samples after I set things up here. Let's see. Just clicking on the image. So I'm going to make pretty big sample boxes. Let's do a high tolerance here, as high as you can get, right? This image doesn't look like there needs to be a whole lot happening to the image. In fact, he may have already done it. I'm not sure exactly. But I'm going to go ahead and just make absolutely certain that it's as good as it can be. We'll do subtraction. If there's anything remaining there, that's fine. And I think that's it. Let's just go ahead and do this, however, and replace the image. That way I can just do it as we go along. Now, for those that are unaccustomed to using DBE on a field like this, if we display this field with a bit more contrast, I mean, there's lots of nebulosity everywhere, right? So how do you know where to click? Well, obviously you click on regions that don't have much nebulosity. I'm going to click over here. And you might think, oh no, Adam, I can see something there. Yeah, so what? You know, the thing is that there's nebulosity and then there's useful information or signal. Just because you can see something in some stretched image, you have to pick some threshold to be able to display data. There may be information that goes all the way into the noise beyond which it becomes useful. So now I'm clicking in areas or regions where the information is not terribly useful. It's not going to be the kind of thing that will ultimately be displayed very well, and that can basically be the background. And as long as wherever I click here, I'm not seeing any stars show up in my box, I know that it's it's going to be a perfectly valid sample. I have a high tolerance there, and that means that, see, I can even do one right here in that little area right there. That means it'll be safe and free from any goofiness that might happen. So, let me be sure I'm zoomed out. Yep, I am. So I might even put one in the corner here, come down here, I'll put a sample, put one in the corner here, put one here. I'm not being very careful at all, and you get the idea. And then what I'm going to do is I'm going to save this pattern and then apply it to all the other images. It'll only take a second. So let's go ahead and apply like this. And we can check and see the background. Yeah, he may have already done DBE here. This background requires very, very little adjustment at all. I'm going to go ahead and follow through with the others. Let's just save this instance here so that I have the ability to apply it to all the others, which I'm going to do now. So I'll be back in just a second. Maybe that's unfair. Maybe I should show that. So I'm going to say cancel this, and just, if you haven't seen what to do, you just double click on the instance that you make, and then it's all set up. The same samples, because the nebula is going to be the same in all of these images, and then I just hit the check mark, and now I'll go and do them all. Okay, so having done that, I've applied DBE to all of them, because I can make a color picture in a moment when we're done. But here is the green image, and what I'm going to take advantage of, as I demonstrated earlier, is the luminance image. The luminance image doesn't have the issue. So instead of calculating a replacement from the luminance in the green from the whole image, I'm going to use just a section of the image. That's a trick. I think that this will be a useful trick to do here. And the tool I'm going to use is linear fit. So linear fit is the matching algorithm that matches both the signal strength and the background brightness. So those two elements, it's a linear fit, that is going to make the images match one another. So let's get out linear fit. We can just at least see the process and have it ready to go. So here's linear fit. And the trick is to make then a preview of the area that is of interest. So we don't need to do the whole frame. We can just do this. We know that the problem is in this kind of general area here. So I'll make a preview like that. And then I'm going to copy this preview over to the luminance. So we have two previews that are identical pieces of the field. And then I'm going to drag them out individually here. So we have a green one, and then we have the luminance. We have two previews. And I'm going to do linear fit on these guys. So I'm going to match these, and then we'll substitute the luminance. That's the one that doesn't have the problem. Once we have matched it to the green, then we can perhaps substitute it into the green image. So the question then is for linear fit. You may have seen it on the answer already on the screen. But the question is, what is the reference image here? The reference is the green one. It's what we're trying to match. We want the luminance to look exactly like a green image here. So we need the reference then to be this green preview, which, so there's a preview. Notice how this is something that I don't know if everyone knows. There's an arrow here, and then there's actually one that's an underscore. The arrow is the preview that's associated with the frame. Literally, it's in the frame, in the view itself. But the one that I dragged out and made it its own image, that's this one. I don't know that it matters. We could probably do the linear fit on a preview, but it's good in this case to have them separate because we're going to do a substitution here in a moment. So that's what we're putting in here, and then we're going to apply that to this luminance here, like this. So it does the math, and down here is the math that it had to do. What's most interesting is the amount that it had to multiply and add or subtract here. So that's what these numbers are telling us. And now let's do the auto stretch on both of them, and let's see if we're going to get away with this. What we want to see is very little variation between these two frames if we blink them. And look at that. I think that that's going to work in our favor. So the luminance looks very much, it has a little more contrast, but it looks very much like the green frame. And if we're careful about this, we can make that substitution work in our favor. So what we're going to do then is I'm going to shade some things here just so we can get them out of our way. Let's do a lot of shading. The most important bit that we want is this luminance preview. This is going to be our substitution image into the green. So we do want the actual green image, which is this one here. And I will shade this because we're going to be putting it into the green. All right. So that is what we're going to be putting into this image right here. And we're going to be putting it into that location. So this location, this preview, actually has some numbers that we need. So if we go to modify preview, I'm going to write these down. It says it's 1440, 2376, because this is where, if you recall, Jonathan wanted precision. Well, this is where the precision comes in. So I wrote down those four numbers. They define this preview in the image. And now we're going to use another thing that I made that I think is really helpful. There are a couple of different ways if you want to substitute one image into another. Pixel math is going to be the means by which we do it, but we need an expression which does this. So I created an expression. It's available to everyone. If you visit my website at AdamBlockStudios.com, you can go to the fundamental section, and under Pixel Math here, you'll find that I make available to anyone, goes to the page, you can see that I've got some expressions. And this is an expression I wrote here that allows for this substitution. Basically, it looks at a rectangular region, it takes one image and puts it into another in that rectangle, which is exactly what we have. So I'm going to copy this, and then I'm going to go back to Pixel Math here, and then we'll paste the expression in here. Now, of course, I actually explain on my site exactly how I made this formula, how it works, how you can make formulas like this to do very, very useful things. In order for this to work, though, I need to define the symbols, and you'll see that I did that here. These are basically the variables that are being used. Oops, Control C rather, and then come here and do Control V. So that's all I did, is I just pasted everything in, and the 4 numbers, that's the origin of the rectangle at this position, XY position. So we type in those numbers, I wrote them down. And then the other 2 numbers are the width and the height of the rectangle, and 1800. That should do the job. Now, you'll see that I have here a placeholder that says image to be inserted. Well, we need to type the image where we are, the thing that we're inserting, and that is this creature right here. So it is called loom, and I need to be sure I capitalized everything just like it is here. And I could have gone to click in the expression editor, but I can type one thing. I think I have that right. So now we do what is, I hope, the fun part. Let's see how well it goes. I'm going to drop this onto here, and it's going to put this image in that place. Ready? It won't. I did something wrong. I think I actually accidentally pasted my little symbols thing in the wrong place here. So let's try this again. Let's do the substitution. And there we have it. So let's look at the before and the after. Isn't that cool? Let's look again. Let's look at the before and the after. Now, I am going to remove this preview, because ultimately what we don't want to see, right, is we don't want to see, let's delete that. We don't want to see our, well, now it's going to say that. We don't want to see our rectangle here show up in the final view. By my eye, I can't easily see it. However, if you want to be extra super duper clever about this, instead of pasting in this entire rectangle, what we can do is make a mask. And here's where the game script would be useful for us. So let's just make a very, very quick mask. Let's do the auto stretch here. And then we can just add an element, and we know our problem area is here. And we can add several elements if need be here, but we can add a big element here, like this, and we can add another element over here. I'm trying, there we go, like this. Give me a second. There, I've added some elements like this. I'm going to go ahead and make this a binary mask, and then we'll just use convolution to fuzz up the edges of this thing, kind of like our feather. I think that that's fair. And then we can apply that as a mask to here. I hope I got all of the areas here. And then we do the substitution. So I'm going to remove this so you can see it happen. And now we do our substitution. And instead of there being a rectangular area, there's just the area of interest where there's no rectangle anymore. There might be some of these shapes that I made, but those are even harder to see. And so then we've corrected the green image. That's it. That's what you have to do. Now I'm going to go ahead and do the same step for the blue image and then create the color image, and we can look at the difference between the original color image and the final color image and see if it actually is a good and viable solution. So here I am, just a quick peek. I did the linear fit in blue, and now I'm making this little mask for the blue bits here. So we do a binary mask, we say OK. There they are. So let's apply this. Oh, I got two of them. I only needed one. Yeah, that's the gradient one. Let's go ahead and do a little convolution of this. Like that. And then apply that to our blue. Like this. Let's look here, show mask. I've already typed in the correct values here. And there they go. So here's the before and after for blue. And now we should be able to do the final thing, which is to create a color picture and see how things look. So let's go ahead and do that. We'll have a, let's see, channel, we already had channel combination. Okay, here it is. So these are still called red, green, and blue. Should be able to just make a color picture. We have kind of a different bias here because I applied DBE, but that's okay. Let's go ahead and unlink, do the thing. And there we go. There might be a tiny mismatch there. I can almost see. Almost looks like there might be a little tiny red bit there. But based on what we had before, that is much, much better. So I'm going to go ahead and run a photometric color calibration on this frame and see if we can get something that is a slightly more balanced image, and we'll call it good. Okay, so I did it. What I did is I created a RGB image of the original data. Now I didn't do the DBE. You can even see the effect of how DBE helps in addition to the correction that was made. So this is the original data as it was given to me, just combined as an RGB image. Now I did solve it using photometric color calibration, but it still has kind of the gradients because of DBE. And then here's the DBE result with the removal, we hope, of those scattered light kind of artifacts. So here's the before and here's the after. You can see maybe there's a hint of something there just because of the fact that the linear fit is not perfect, and so it does change maybe the color balance in that area a little bit, but I think that that's workable. And I think that this is an excellent solution. I just now noticed there's some blue stuff over here that I didn't take care of at all. So there you go. That's what it looks like when you don't take care of it. You can still see it in the final image. So I hope you enjoyed this session of problem solving. It's a relatively dramatic one. You can fix an image effectively because you can isolate the issue, and then that gives you the opportunity to employ some fairly precise and maybe even elegant kinds of solutions. Thank you very much for joining me today, and I hope you'll watch more of these YouTube videos that you find on this channel. Of course, I also want to encourage you that if you like videos like this, become a member of AdamBlockStudios.com. Until next time.